Yes, class. Good evening. Am I audible to all of you?
Yes.
All are present right now. Avia, Fahad, Rifat, Sahal, and Wafia. Sahal, where were you? Only 2 classes you had taken, then you weren't present. What happened?
Yes, ma'am. I was traveling throughout the period and I was in India.
All right.
Yeah.
Okay. So we had ended with current electricity. So Sahal, do you want the recordings of current electricity or what? Just let me know.
Yeah,
Or
it will be
you
better.
want to take the backup classes because in one batch current electricity is still going on. So whatever
No,
suits you.
no, it's fine. I'll take the recorded classes.
You'll take the recorded class, no?
Yeah.
So okay, fine. And Abia, regarding your paper, I didn't receive your paper on mail. So Abia, if you can send me the paper on WhatsApp today, or if you can attach your document in the chat box today only, then also it's fine.
Ma'am, I didn't give that test.
Okay,
Test
okay,
of
okay. Yes, a test was there, no? Last test we had on drift velocity. Yes,
yes,
drift
ma'am.
velocity, So you didn't give the test. All
No,
right.
ma'am, I did not know about it.
Okay. Okay. Yes. I think you took the screenshot and then you left, no?
Yes, ma'am.
Alright, okay. I was searching for your paper. And Abhi, one more thing. When the meeting ended, no, last time, the doubt that you were asking last time, that
Yes, ma'am.
also got erased. So that's why I was not able to. I had told Fahad his solution, whatever he was asking, but yours I forgot. So if you can write it again, or it's better if you send me on WhatsApp. Just
Ma'am, I don't have your number.
on the group. You're not added on the group.
No, ma'am, I'm not added.
So still not added.
Even me, ma'am. I wanted your number, and if there's a group, you can add me to.
Okay. Sahal and Abia. Sahal, I remember, but Abia had mentioned them. Okay. Abia, I'll mention you. Then you'll get my number from the group only. Yes, Fahad, you had some doubts in the assignments, no? Which assignment? The last assignments that you had, no? Samia has also joined. No, you people had given the test. Let me show you your papers. Most of you, I think, have done well. Rifat is present. Okay, assignment 4 and 5. So, Fahad, what you can do, you can send me the question. Just send me the question on WhatsApp. You have my number with you. Or it's better if you send it on the group. Others will also see the question and see the solution. Whatever suits you, just send the screenshot of the question that you had, the way you had sent it previously. Similar to. Right? Tell me the question number, I'll send you the solution. So, whose paper is this? Rifat. In Rifat's paper, I think derivation part only. See, derivation Rifat. The rest of the things, numerical and everything was fine. Everything you've calculated perfectly, just the derivation. Just see and revise the derivation ones. Shamia has joined? No, Samia has joined. Shamia's paper, what was the error in her paper? Derivation is fine. Okay, current density. Yes, I remember Samia. You had an issue also in current density, no?
Yes, ma'am.
See, current density is basically current divided by area. So in the first part, I think you have calculated the current already. You have the value of current with you. I think which you have calculated, that's right, 2 into 10 to the power minus 2 amperes. You also have the radius from the question. See, radius is given to you as 10 to the power minus 4 meters. So J will be what? Current divided by area of what? Area of cross section. Area of cross section means if this is a wire, area of this end, this is known as cross section. This is known as cross section. This is the length. So you don't have to take the area of the whole wire. You just have to take the area of this section. So what will be the area if radius is given? Current is 2 into 10 to the power minus 2. Radius will, area will be pi into r square. This will be ampere per meter square. Clear?
Yes, ma'am.
Rest of the thing was fine. Did Reem join right now? Reem. Madiha has also. Madiha gave the test, I think. Madi, did you give the test?
No, ma'am, I didn't attend the class last week.
Okay, okay. Yes, it's class. There. What happened to Fahad? Yes, Fahad, in your derivation. Rest of the things, Fahad, you wrote it perfectly. Rest of the things you were able to write it. See, Fahad, in the derivation, this derivation portion, you have not mentioned, you have mentioned the terms at the last. See, you have to write everything. You have to write, consider a wire of this section like this, like others have also written. In the derivation, you have to show the diagram, the figure that the way I draw it. Because in the board examination, if it is for a 5 marker or a 6 marker, usually drift velocity, if it comes, it comes for a long, in your long questions only from your section D. So the way we did it, no, for average velocity for every electron is u1 plus u2 divided by n. Then at the last, you show it is coming out to be 0, this step, this one. Then you show it at the last. The rest of the things were fine, just see the derivation once again. Z, Bafia, I think Bafia shown, no? Madiha didn't. So see students, whenever you're attempting the test, no, then whenever you're attempting the test, just make sure you revise the derivation portion well. So I think all the students that are present today, I've shown you your paper. All right. So magnetic effects of current. This is your chapter number 4 of NCERT, moving charges and magnetism, by the name it's written. So basically we call it as magnetic effects of electric current. Now in this, the first concept comes is the concept of magnetic field. I'll send you the video lecture also today. Electric field. So anyone who wants to revise, you can revise. Electric field is what? Electric field, we had seen, it was the space around a charge where electrical properties could be experienced. Electrical properties, what do I mean by electrical properties? Forces of attraction, forces of repulsion, all the forces that are occurring. That we call that space around a single charge. We call it as the electric field. Similarly, when we come to magnetism, in case of magnetism, if a magnet is present, let's say a magnet is present, magnets have the polarity north pole and south pole, then what is meant by this magnetic field? Magnet is present, but what about this magnetic field? See, regarding this magnetic field, the space around the magnet, that we will call as magnetic field, where magnetic properties could be experienced. Like if this is your magnet, there will be some space around it. All right, where magnetic fields are beginning, magnetic fields are terminating, and everything is occurring. Now, if I bring another charge, another magnet over here, north pole, if I am bringing till this distance where it is touching the magnetic field, then only I'll be able to see the repulsion, because like poles are there, so obviously they will repel each other. Or if I bring a south pole, south polarity magnet pointing towards the south polarity, that will attract it. So at a certain distance, I'm able to feel this. If I have two magnets, let's say if I have two magnets, if I keep them at this separation, will they be able to show repulsion or attraction? When I'll bring them closer, then only they'll be able to show either repulsion or attraction based upon their polarities. Now, how are they able to show it? Because of the presence or existence of magnetic field. Suppose, let's say this is a magnet. When I'm bringing it till here, then only I'm able to get this attractive force. When my hand is placed over here, I'm not able to feel any kind of attraction or repulsion. So this space, no, till this space where this magnetic property I'm able to feel when I'm doing this experiment, that is the space around the magnet where magnetic properties can be experienced. So that space we call as magnetic field. Electric field for charges, magnetic field for magnets. Fine. Now, how do we represent magnetic fields? Magnetic fields, this is represented through capital E. In electric field, we show it through capital E. The letter E is there. Magnetic field, it is not with M. Remember, because many students, when they read the questions, they get confused between magnetic moment, magnetization, intensity of magnetization, and magnetic field. These terms few of these terms you will see in the next chapter. But magnetic field will be constantly used. You'll see the direction, you'll see all this. So this is magnetic field. Obviously, it's a vector quantity. And this vector quantity doesn't get resolved by just looking at the direction of parallelogram and everything. These vector quantities, we have specific laws and rules for it. Special laws are there, special rules are there. We'll be using, you must have heard of also of this Fleming's right hand rule, Fleming's left hand rule, right hand thumb rule, right hand palm rule, left hand thumb rule, and all these. So what we will do, we will just be using our right hand in different ways to get the direction of magnetic field according to the situation that is present. We will not be confusing it with our left hand or any other, because at the end, what represents in your left hand might be the quantity that would be representing your thumb in your right hand. So ultimately, this becomes very confusing. So we'll be just using our right hand. That rules and laws I'll tell you. But remember, magnetic field is a vector quantity, and I'll tell you, a test was conducted in other batches. Magnetic field was asked, and specifically magnetic field's magnitude and direction, both were asked in that test. Maximum students have just calculated the magnitude and have left it. Some students were there who could calculate the magnetic field's magnitude as well as the direction whether it was asked or not. So remember, it's a vector quantity. Your answer will only be complete if you write the magnitude as well as direction. That's why continuously, whenever we were using electric field and any quantity regarding current or anything came, we used to write I cap, J cap. At least that shows the direction. It is pointing outwards, inwards, or what. So it's a vector quantity. And other thing that you have to remember is its SI unit. SI unit is called as Tesla, which is represented through capital T. So you will see magnetic field like 4 Tesla, 5 microtesla, 3 Tesla in this. That's the magnetic field. Now CGS unit for it is Gauss. This G represents Gauss. That's the CGS unit. This is the CGS unit. All right. So CGS unit for magnetic field is specified, which we call it as Gauss. Now this conversion is used. 1 Tesla is equal to 10 to the power 4 Gauss. This conversion is used in the numericals. Like there were many, when we did electric charge, that topic, electric charge, the first topic when we did, what did we see? We saw that the SI unit of charge was Coulomb, and the CGS unit of electric charge, it was electrostat Coulomb or electrostat unit, stat Coulomb, and all these. And the conversion of Coulomb into these was never used by us in any of the exams, if you see, in any of the questions, if you see. But this conversion regarding Tesla and Gauss, this is used a lot. Many a times Gauss will be given, and most of the time, maximum times Tesla is given. So do remember it. Now, in magnetic field, we cannot only conclude it till here. We have to find out what are the sources of magnetic field. Now, regarding the sources of magnetic fields, sources of magnetic field means what all quantities exist in nature that can produce magnetic field. For example, if I talk to you about the hematite ore or the magnetite ore, this is an ore which is extracted from the earth. So this is the natural source of magnetic field. You must have done these formula, Fe2O3, Fe3O4. In your chemistry classes, you must have heard of these. So these are what these produce the natural magnets. Natural magnet is obtained from them, from the earth. There's a separate topic, earth magnetism, that has recently been deleted from your syllabus, but earth magnetism also involved. We'll do it at the end. We'll do all these topics. So earth magnetism also, it means when earth acted as a magnet. The way we did no capacitance, if capacitance acted as a conducting sphere, similarly. So first source is this. Second source, see, current carrying wire. If you have a wire where current is running above, downwards, whichever manner, if you have the current flowing, then you will experience a magnetic force surrounding it. There is a presence of magnetic field. So that's another source of magnetic field. One more source of magnetic field. This can be this magnet electronic spin. I'll tell you what is meant by electronic spin. You people are in class 12th, so when you were in class 11th, you must have done that lesson. I don't remember, it's periodicity or whichever lesson in your chemistry, where any electron with the shell was given and you had to identify all the components of it, whatever is the amount of N, P, and something like this. So there you must have done. You used to write M also, either as minus half or plus half. Remember? Does anyone remember this? Have you people ever done this? Minus half spin of electron, which we call minus half or plus half. You write one of them because obviously electron cannot spin in two directions. For the single electron cannot spin in two directions. So electron spin, this is known as electron spin. I don't know if it is still included in your chemistry syllabus or not, but I think you people must have heard of this. Yes or no? Anyone? Electronic spins.
Yes, ma'am.
Yes, you've heard, no? All right. So those electronic spins only. So when the electron spins in its orbit, then it also produces magnetic field. So these are certain sources of magnetic fields. Do one thing, first note down this. Questions from magnetic field do not come directly. That I'll tell you how do the questions come. The way electric field questions came, no, not in that manner. That is related to your chapter 5th. That we'll see later on. This chapter is medium. It's not very hard because you have already done electrostatics. So many things get revised, like magnetic field, electric field, you have understood. So magnetic field is just that you have to take the analogs in magnetostatics. The next chapter is the easiest if you understand this chapter well. In this few derivations you have to remember that can be lengthy, and the formulas for different. Otherwise, once you remember the formula, the whole question solving part is easier. So it's not very tough because you've already done and dealt with electrostatics. Done. So if anyone is writing, just stop me, then I'm moving further. Now you have one experiment which is known as Oystead experiment. This experiment is not included in your course. So you need to even do that. I'll just tell you in brief what this experiment was. Basically, Oystead experiment. He took a pointing needle. All right, that needle of a compass that we use, and at one end of it, he colored it and marked it as north. Now, what did he do next? He, in order to get the concept of magnetic field, he wanted to get the concept of magnetic field. So what did he do? He kept that needle on a pointer. He balanced it on a pointer, and then he connected a circuit along with it, with a cell using proper wire, keys, and everything. A circuit was connected above that. He saw that as soon as the key was tapped in, the key was basically tapped in, means current flowed through the wire, north pole deflected, slight deflection was there. And when you stopped it, then he noticed that the needle didn't deflect in any direction. So needle of the north pole gets deflected in which direction? That was also mentioned. If the current flows from south to north, then the needle of the north pole gets deflected towards west. And if it goes or moves from north to south, then the needle of the north pole gets deflected towards east. You don't need to remember in any of these things. Just remember that when Oersted conducted this experiment, he saw that whenever current flown through the wire, this whole circuit, because of the current, there was a deviation or deflection in the position of the needle. And as soon as he stopped it, the needle returned back to its original position. This you just have to remember. Now you have one major law which is known as Biot-Savart's law. This is an important law which you have to remember. Now, before moving on to what Biot-Savart's law is, just understand the terms. Terms I've already written because the time gets wasted if you write everything again. So I've written these terms again. Basically, what did we do? We had taken a current element, this curved line which you are able to see, AB. This is a basically wire that I'm taking. A wire like this. No, wire like this. Then a very, very, very small section between this wire. If this is the wire, no, in this wire. Such a very small section in this wire I've taken. So obviously, if current is moving in the main wire in upwards direction, in the current element that I have taken out, the current will again move in the upwards direction only. So that small element which I have taken, no, this element, this element, this small, very small element, this is basically known as current element. What is meant by current element? Current element simply says that a wire is there. If you take a very small portion of the wire where current was flowing, so it will be having the same direction. So we call it as the current element. Basically, it's a length. We call it as current, but it has the dimensions of current. So this was the main wire. This is a small portion of it. All right. Now, we have to find magnetic field at a random point, because using this law, we'll be having different shapes, sizes where we have to calculate the magnetic field. So, magnetic field we have to calculate at a random point. This is a random point, and even it is making an angle of theta, random angle. So, angle is made between what? Angle, I'll tell you. See, the separation of current element from this point that we are calculating, that we have taken it as small r. So small r is what? That's what the first line has been written. Small r is position vector of P. P is a random point where we are calculating. P is a random point where we are calculating the magnetic field. Separation of the current wire. This is the whole wire. This is a point. This whole separation, we are taking it as R. This is the current wire. This is the
Means it's
smaller.
distance. Means R is the distance, right?
R is the distance. Exactly. R is the distance. That, and this R will be used everywhere depending on it. And it will be zero when? Only if it is overlapping. But we will never overlap it because we'll always try to find out it at a particular point, at a random point. It can be making an angle of 90 degrees. It can be making an angle of 180 degrees, any angle. So to generalize it, what did we do? We just took an angle random. This random angle by itself we have taken. This angle theta. So angle theta is what? Theta is the angle between the current element and the position vector. First tell me, are these terminologies clear? Then only you'll be able to understand Pvt law, because in Pvt law there is no derivation. There is no derivation. You just have to understand that. Any doubts in any of the terminologies that we are going to use? Just ask me, I'll explain again.
Ma'am, can you explain current element again?
Current element. All right. See, current element is basically, it's like I have a wire. All right. See, it's a wire. Current is flowing, let's say in this direction, whatever is this direction, current is flowing. Now, what did I do? There must be some complete length of this wire. In order to find out the magnetic field at a particular point, we take, because Pvt law is done experimentally, so that's why it's not that we are taking. Basically, it was a law that was stated. So he cut a very, very small section. Very small section. So length will obviously be very small. And then he called it as DL. DL means what? A very small length only. A very small length. So this length is known as current element. Now what I was trying to tell you is that current element sounds like as if it's current. We are talking about current. No, it's just the length, a very short length. SI unit will be meters only. It's just that whatever will be the direction of current in the whole wire, that will be the same direction in this small part. In every part, if you take, the direction will be this only. So even if you take a very small part, the direction will be pointing in the same direction. So that's known as current element, because this will be used. DL will be used a lot. Where we use DL because we integrate it and then find out the length and the current that is flowing in the complete wire. If I know what is the value of this DL, if I integrate it, I'll be able to know the complete length. So that's why we choose this small term DL. Clear, Sahal?
Clear, ma'am.
Fahad, you were also asking something, no? Fahad, you were also asking something. Oh, clear.
Yes, ma'am. Can you explain that point P?
All right, point P. See,
Like it can be in any direction. Or
any direction, any random. For example, take the example of this needle only. All right. So you wish to calculate the magnetic field at this point, P, random point, any point. And let's say this is the current element that I have taken. A very small portion from the wire only. This can be a current element. So this becomes the position vector R. And this is the point where we are calculating the magnetic field. Suppose, let's say I want to calculate the magnetic field here. This is my point. And the current element that is present is, let's say this, some other current element is there. So where do I want to calculate the magnetic field? At this point. So this becomes my position vector R. Just join it from the current element. This is my position vector R. This is DL. So DL is, let's say current is moving in this direction. So DL will be like this. So this becomes the angle also, and anything that you want. Yeah, P is basically the point where you have to find out the magnetic field. There will be different points. Like if you curl your wire, suppose you have the whole complete wire with you. This is a wire. And if this is a complete wire, if I make it in the form of a complete circle, this is not symmetric, but if I want it, then what would be the magnetic field at a random point, let's say at the center of the circle? At the center of this, at this point of the circle, there can be a value of magnetic field. So that becomes my point P. Point P you can vary by yourself wherever you have to find out the magnetic field. Clear?
Yes, ma'am.
And to others, clear to all of you? Any doubts? And again, then I'll tell you what was the actual Biot Savart's law. All right, if it's clear. Now, see, according to Biot Savart's law, what did he say? He did some experiments. Certain experiments he did that are beyond our scope to study right now for your class 12 perspective. He gave 4 points, mainly 4 points. According to Biot Savart's law, he said, since we are talking about a very small current element, let's take dB or let's take complete magnetic. He said that the magnetic field, no, that will be produced at that point P, whichever point we have taken. That magnetic field, it is directly proportional to the current flowing. So this is directly proportional to the current flow. Current flowing in the wire. So magnetic field is directly proportional to the current flowing in the wire. Second point that he gave was magnetic field is also proportional to the current element dl. And obviously this you can relate. If it is proportional to current, then obviously a small portion is taken. It will be proportional to the length also, that small length, because the current's direction and the dl direction is same. So these points are interrelated. Remember I told you angle is also formed. Angle's value can be different for different materials. You can put it 0 where you see P is directly like this. And if you're able to see that L and P, both the points are like this, you can put it as 0. If you see DL is this, point P is coming like his, you can make it at 90 degree, whatever you wish. But what is theta? It's the angle between the current element and the position vector. As you can see, this is the current element, basically the wire, and the position vector, this. So Biot Savart's law says that magnetic field is also proportional, directly proportional to the sine of this theta. For example, let's say they are making an angle of 30 degrees. So you will be using sine 30 degree. And what is sine 30 degree? Half. So magnetic field is directly proportional to half. Like this, sine 30 degree proper, whatever trigonometry you have studied, that sine will be used. Last, it says that magnetic field is directly proportional to 3 things that we have seen, but it is inversely proportional to the square of the position vector. Can you recall? We did this. Coulomb's law was similar. Inverse square rule it followed. Even in case of the electric field that we concluded, electric field were also inversely proportional to square of distance between the charges or whatever charge was present. Similarly, magnetic field is also inversely proportional to the square of the position between them. These 4 things are there. Now, if we combine all of these things, magnetic field will be equal to what? Not equal to, will be proportional to I dl sine theta, proportional to 3 things, inversely proportional to square of distance between them, r square. Now, how do we remove this proportionality? This is not helping us in any way, so we have to remove it. Let's say we have put a constant k, random k we have taken, I dl sine theta divided by r square. But now we have to elaborate and focus on what is the constant that is coming. Rest of the things you have understood, proportional to 3 things, inversely proportional to a single thing. How is this constant? What is this constant? Is this constant still 1 over 4 pi epsilon naught that we had seen in electrostatics when we using electric field or Coulomb's law? Or is it a different variable? See, 1 over 4 pi epsilon naught, which was 9 into 10 to the power 9, that is used only in case of electrostatics. If you have magnetostatics, magnetics, or any of the section that covers magnetism, the constant that we use is mu naught divided by 4. Now, what is mu naught? Mu naught is basically permeability. Epsilon was what? Epsilon was permittivity. It allowed the different media to influence the electric force that we had seen in Coulomb's law. Now, let us just focus on this constant. Let us just focus on this constant. This is 4 pi mu naught 4 pi epsilon naught. So the formula of Biot Savart's law also becomes mu naught divided by 4 pi IDL sine theta divided by r square. This is the formula, and Tesla you can add it by yourself. Now let's just see this, the constant that we are getting. First thing, in this constant k is equal to mu naught by 4 pi. This value, this whole value is equal to 10 to the power minus 7. The way constant's value was what? 9 into 10 to the power 9 in case of electrostatics. In magnetics, this value is 10 to the power minus 7. So if you are asked to write the value of mu naught, you will write it as 4 pi into 10 to the power minus 7. You can even solve this. 4 into it will come out to be 1.23 something. And the way epsilon naught's value is fixed, no, 8.85 into 10 to the power minus 12. Similarly, you have this value 4 pi into 10 to the power minus 7. But in most of the questions, pi is already there. So we don't remove this. Pi gets cancelled in the question. That's why just learn it like this only, 4 pi into 10 to the power minus 7. In whichever question you need the value, no, then you can put the pi's value as 3.14, however it suits you. So this is permeability. Now let's focus on this constant, that is mu. So this is clear, this is mu naught, and then you can add the unit Tesla meter per amp. This is the unit of dimension and everything you can calculate. Now let's see the permeability. Basically this mu is the permeability. Permeability is what? Something that allows, using the word permeable. Most of the bio students have used this term permeable. So permeable is what? It allows something. This is similar to what you have studied epsilon, permittivity in case of free space, in case of electrostatics. It's similar to it. Right now what is happening? Magnetic field exists. Let's say for glass, a bar magnet is present. It is weakly acting because of the water surrounding it, because of the water. But it will be still able to attract slightly because the permeability is less. It is not allowing the electron, the bar magnet to act. That's we call it as permeability. Allowing in different medium, allowance of magnetic field or governance of magnetic field in different medium. If you are talking specifically about permeability of free space, permeability of free space, which you call air, then this value is 4 pi into 10 to the power minus 7. And if you have a different, if you take the ratio of all these, no, mu by mu naught, this term we call it as the relative permeability. Relative permeability is when you compare two media. One with respect to what? With respect to air only. See, I'll repeat permeability once. Constant by Savart's law, the laws, the formula you have understood. Formula, remember it. That formula will be used throughout. Not only in this, in the next chapter. In case of, like in last year when you were discussing rotation motion, when you had that lesson rotational motion, what did you do? Force became torque. Linear velocity became angular velocity. Linear acceleration, it became alpha, angular acceleration. Even displacement became theta. That was the angular displacement. What did you do? Everything was the same. It's just that it was an analog in case of rotation. Force, the work that force does in case of translation motion, that work is similarly done by the torque. Similarly, the way we have studied permittivity allowed or change the value of force according to the materials. This way we have permeability in terms of magnetics. It allows different media to have different values of magnetic field and act accordingly. Mu is permeability of any medium you take. Mu naught is permeability of free space. Specifically for air it is fixed. Free space or air you can write, and this you can write for any medium. If you compare it, That will be relative permeability. Absolute means something independent. Relative means you are comparing it with anything. So that is known as relative permeability. From this permeability, magnetic permeability will be a separate topic that we'll do when we'll come into chapter number 5, the lesson after that. So for now, just remember this term mu naught. This will be used. And one more thing. We'll do certain terms like ferromagnetic substances, we'll do diamagnetic substances, we'll do paramagnetic substances, we'll do all those who were there in the group. You must have seen I've sent a table. That's for other batch students. You will also learn from that table. Their classification of magnetic materials have been. So what happens? Different materials have different values of permeability. Like for iron, I've written it's the relative permeability is of order of 1,000. For diamagnetic substance, it is even less than 1. That becomes point something or what. For ferromagnetic, it is greater than 1. So greater than 1 can be between 0 and 1 also. Any value like this. So for different, you don't have to remember this right now. You have a full chapter on permeability. Not a full chapter on permeability, but a whole section on permeability. Because you have these materials and their classification in your syllabus this time. So permeability, don't go into the details, but remember the constant. Constant is mu naught by 4 pi, which is equal to 10 to the power minus 7. Wherever this constant is required, we'll be using this constant as it is. Now, one more thing. In vector form also remember, if you have to write it in vector form, how will you write it? In vector form, it becomes, see, mu naught by 4 pi is there, the constant. I is there, dl cross r becomes divided by r cube. We just write it in vector form. It can come in your 1 marker to write it in vector form, but this vector form is not used because you'll open dl sine theta, dl into r into sine theta. R will again get cancelled with this r cube. You'll get the that statement what we did the formula back, ideal sine theta by r square. So it's just that for your knowledge, and if it is asked in any of the exam for 1 marker, you can use vector form if it is. One last point before you take a break and note down everything. Just in case if relative permeability is mentioned to you, Biot-Savart's law formula, IDL sine theta divided by 4 pi here r square, this remains fixed. Mu naught also is there, along with mu naught, mu r also gets multiplied if a different material is used. If it's the magnetic field, we are calculating in a different medium. The wire is placed in, let's say, glass or something, different medium. Mu r is what? It is the relative. So a lot portion we have covered. Direction and everything I'll tell you later on. First, note down the Biot-Savart's law. This is an important law and this is the basis for your all the questions. And from this lesson, Biot-Savart's law is must coming in your exam. And no need to write that Oersted experiment from here. Permeability means it has something. Not exactly that it has something. Permeability means that it gives you a measure of magnetization. If, for example, if you have an iron ball with you and you start rubbing it with a bar magnet, so what will happen? A certain time will come that the iron ball will also get magnetized. So that measure of magnetization, that measure of magnetization that a material is obtaining to respond to a magnetic field, that we call it as permeability. For different materials, it's different. For copper, it's different. For nickel, it's different. For zinc, it will be different, and all those. Or then in magnetic, there's the next chapter, magnetism and matter. There we'll see it's the ratio of magnetic induction and magnetic intensity. So magnetic induction and intensity right now we haven't done. So you can just understand what permeability means is that if magnetic field is there, how much magnetic field is getting into the substance, penetrating through a material. This you can remember. Or basically how to measure a magnetization that a particular substance is getting in response to. Yeah.
Ma'am, what is ferromagnetic?
See, ferromagnetic substances, these are actually magnetic substances only. They have certain properties that you will see later on, like they are strongly attracted by magnetic field, how they move from the stronger to weaker sections or weaker to stronger sections of magnetic field. Certain properties are present in them. We'll see certain terminologies. Let's say this only. Let's take the example of permeability. So ferromagnetic substances become those substances that have the permeability in this range. That differs it from the diamagnetic. Classification is necessary. Even if you have magnets with you, there are different materials, there are different magnets present. So you need to have a classification system in order to categorize them. That system of classification, how to categorize those materials, they are grouped into three categories: diamagnetic, paramagnetic, ferromagnetic. Now, all of these will be having certain properties. That's why we have classified them. So one of the properties on the basis of which they have been classified is magnetic permeability, whose value are these values. Mainly, this is not the first property or the main property for the basis of classification. Basically, it's how they are repelled in magnetic field, how they're attracted in magnetic field, how they're attracted towards magnet. That's clear.
Yes, ma'am.
Written, all of you?
Yes, ma'am. Done.
Just a minute, ma'am. Done, ma'am.
Now the direction of magnetic field. This is very important. Direction of magnetic field. See, for the direction of magnetic field, we'll be using right hand thumb rule. Basically, whatever direction you will get, you will see that it is perpendicular to the position vector and current element. Forget that point right now. How to use it? Let's say we have a current element. This is the current element. What are we saying? What does it say? Hold the wire in the right hand. This I'll also mention it. Most of the times, most of the students are right-handed, so they write with their right hand, and whenever the questions come, they start using their left hand and get exactly the opposite answer and the direction. So just be careful whether you're using the correct hand or not. If you're using your right hand for writing, then writing purpose, and drop the pen and then do whatever is the direction and everything that is written. Secondly, it says what? There are different rules for it. We'll see two rules first. Okay, you're a left-handed person. All right. So for you, it's easier because your right hand is always free while writing. So any other lefty? Only Fahad. So two methods we'll see. First method, I use the second method most probably, but first method is also easy. You will be able to do. It says hold the wire in the right hand such that thumb points in the direction of current. What is meant by this? Let's say this is the direction of current. All right. See, this is your wire. Fine. This upwards is the direction of current flow. So you have to take your hand, and let's say a point is also mentioned. A point, let's take this point. This is a point at this is my P point right now. Just imagine. I'll tell you on the screen as well, but just imagine how to get it. This is a random point, P point, that I've taken where I have to find out the magnetic field. Now at this point P, current is flowing upwards. You have to hold it in such a manner that your thumb points outwards. So thumb point outwards, no? Basically thumb points in the direction of current. So current is flowing upwards. So I should keep my right-handed thumb upwards. So this becomes the direction. In any position I can keep my thumb. Now which position to decide whether I should keep my thumb like this, or in which manner? Basically, the curvature of fingers should point along the magnetic field where you have to calculate. I wanted to calculate at this point, so I will curl my fingers towards that point. This is the see, if I keep my thumb like this, if I curl it from here, my fingers are pointing to this point. I won't get it. I have to get the magnetic field at this point. This point means for me it's towards the left hand side. I don't know in the camera what it's coming to you people, but for me it's in the left hand side. When I'm putting the thumb or placing the thumb like this and then curling it, the curling is pointing where? Towards the right hand side. If I keep the thumb like this and then if I curl it, now see, do you see the curvature of the magnetic field? What's the curvature of magnetic field? Complete curvature like this. This is the curvature. Whatever point you have to choose, that will give you the direction. I am repeating it. Let's say this is the direction of current pointing downwards. Keep your thumb along the direction of current. Curl your fingers. Curling of the fingers gives the direction of magnetic field. Now, how to decide what's the direction of magnetic field? This you have understood? Just tell me at least this much part. You have to keep your thumb along the direction of current like this. If this is downwards, then this will be. If current is like this, you have to keep your thumb like this. Current is like this, moving, pointing towards the right hand side, you have to keep your thumb like this. Yes, Samya, that only. Same thing that you did in 10th. Same thing that you did in 10th. So if you're able to recall, then it's very good. Same thing, just recall it. Same thing. So, or let's say current is pointing towards left hand side, so my thumb will be like this. But now how to choose the curvature of finger? How the curvature of fingers will decide the direction of magnetic field? That depends on the point that you have taken. Suppose this was the current that was pointing upwards. Thumb is placed like this. Curvature is like this at this point. Where are my fingers going? See, for me, they are pointing towards me. It means out of the screen, away from you people, it is pointing towards me. Means outwards. That becomes the direction of magnetic field. Let's say this point is the same. At this point, I have to calculate. This was the curvature, no? Curvature, curl will be the same. This becomes the curl. Curvature is this. This is the curl. So at this point, what is happening? At this point, my fingers are pointing towards you people, means into the screen. So that makes my magnetic field inwards. Now I'll show you it with the help of the screen that you have done. Now this is his current iPhone. All right. Now do it along with me. Whatever device you're using, laptop, mobile phone, whatever you're doing it, do it in the same manner. Let's say I have to find out the current in this point. A point is there. If I keep my thumb like this and I curl it at point A, my fingers are pointing towards me. Means out of the screen. Screen is this. This is the screen for me. At this point, this is the thumb kept along the direction of current. Curling of fingers are curling towards me, pointing outwards. This shows that here the magnetic field is pointing outwards. You put a dot and circle it, that shows outwards. Magnetic field. Let's take a point B over here. B point? No, this is not B point. B point is here. So B point, this. Fingers are curling fingers, lead me towards the screen, into the screen, means into the page. So magnetic field lines are inwards, and inwards is represented with the help of cross. Now, let's all do it together for the clarification. All of you, just tell me what is the magnetic field at this point. Do it right now. Whoever gets confused, it's fine. That's why I'm asking you to do it. Wherever the confusion is created, I'll explain you again. Do it. First try. Write me in the chat box. Inwards, outwards. Where your fingers are pointing. Okay, Sahal has answered. Matiha has answered. Wafia. Rifat. Same rule you people have used. See. Now the current is pointing where? Upwards or downwards? Current is now flowing downwards. My thumb will be this. What's the curvature of finger? It means fingers are pointing inwards towards you people at A point. So at A point, inwards is right. So Wafia and Sahal, both of these got the right answer. Madiha, Samia, Rifat, and rest of you. Did you understand or not?
Yes, ma'am.
Understood? So this will be C downwards. At A point, if you do it, then it is pointing inwards into the page, and inwards has this symbol cross. Now all of you try and tell me for this B. Madiha, Rifat have answered. Others, try. Fahad, you also try. See, remember, this time current is flowing upwards, and at B point you have to find out. Others also answered. See, current is pointing outwards. This will be point A. Point B is this. Again, it will be inwards. My fingers are pointing inwards again. This is again inwards. Thumb upwards. This point was point B. All of you, now try this point and please try to reduce the error this time. This is the point B. Why do we call it inverts? When the field is moving opposite to us and vice versa. See, it's not when it is moving opposite to us or what. You have to see because the screen is in front of me, no? So that's why you might not be able to understand. Sahal, try it right now. The answers that I've told you. For just try it for this. Look at this. I kept my thumb like this and the fingers pointed into the page. That's why I called it inverts. What was your doubt, exact doubt? It is not that it is moving opposite to us. It's moving opposite to us. It means it is moving into the page. So that will be what? Inverts. You talk everything with regarding the page. Regarding the page, the sheet, whatever. That is known as inwards and outwards. So if it is moving towards me, it means it is moving away from the sheet, out of the page. So that's why we write outwards. When it is pointing towards the screen, into the screen, then we write it inwards. And obviously, if it is moving into the page, it will be away from us. Clear, Sahil?
Clear, ma'am.
This answer, who has done? Samia, Fahad, Wafia. And Abia also, Madhi also. All of you are correct. All of you are right. It will be outwards. It will be outwards. This is the direction of thumb. Fingers are moving out of the page. So this will be outwards. This will be outwards. Similarly, this also you can try. This A is this. Again, it will be outwards. So understood the first method or not? This is the first method noted till here. All right, Sad, I'll add it. Thank you. See, I'm not starting with the second law or something. We just revise the cross product because cross product will be used. So if two vectors are there which are inclined or subtending an angle of theta, the cross product of these vectors is given by the magnitude of one, magnitude of other multiplied by sine theta. Now, whatever things you take clockwise, you will take it as positive, and anti-clockwise, you will take it as negative. What is meant by this? Basically, this means like I, j, and k cap, all these three have been drawn. Move clockwise. This is how we move clockwise. From I to j. It means I cap cross j cap is k cap, the third one, whichever is there. Sign will be positive. Why? Because we are moving clockwise. All of you must be knowing this. It's just that I'm doing a very slight revision for all those who have forgotten it. Then j cap to k cap. This will be whatever is the left portion, I cap, sign will be positive. Then k cap into I cap. This will be j cap plus j cap. Now, if we reverse it, if I move from j cap to I cap, then it will be k cap but with a negative sign. K cap cross j cap will be minus I cap. Similarly, I cap cross k cap, this will become minus j cap, like this. So just note it down and revise in once come. Then second method and everything, I'll start from the next class. So just note it down, text me when you've done. Yes, for vectors, for cross products, basically this much is there. For vectors, you have the whole complete laws, parallelogram law, triangle law, polygon law, those different, mainly parallelogram law is used. For cross product, this is enough. This much knowledge is enough. Others have also done. Avya, Samia. All right, class. So I'm stopping here today. Those who have completed the writing portion, you people can leave. We'll meet on Thursday. All right. Take care. Bye-bye.
Thank you, ma'am.
Thank you, ma'am.
Thanks, ma'am.